Okay, anybody have any questions from last time? Uh, so we talked about the five quantities that you use to define waves. We did one problem showing how you might have to, connect those things in a problem. The next thing I want to talk about is how waves combine. So you can think about like, when you're at some kind of event or whatever, and people clap, like each clap is making a sound wave. How do they combine? Like the sound that you hear in the stadium is different than what you hear from like one person clapping. And to talk about that, we have to be really clear about what we're graphing, like what we're looking at when we look at graphs of waves. There are really two types of graphs that we look at. So think of the graphs that represent waves. So a wave, an oscillator is like a point that's position changes in time, right? So when you look at the graph of an oscillator, it's pretty clear what you're looking at. You're just looking at how the position of that single point changes as time goes by. With a wave, though, it's more complicated because you're not looking at a single point. You're looking at a line of infinitely many points. Or even in 3D, you could be looking at a whole space of points, And so what do you choose to plot? Well, you could think of doing a complicated 3D plot, but that's not what we're doing. We look at graphs of waves in two ways. We look at a position versus time graph. And this is a graph, so if we're looking at how it changes in time, and it's a whole line of points that are changing in time, how do we represent all these points? You know what I mean? And the answer is we don't. We choose a single point to look at, okay? So you could choose, and remember that all of these points along the line are oscillators when the wave is going. So basically, we're just choosing one of those infinitely many oscillators to plot, okay? So this graph represents a single point along the wave's path. And what does that graph look like in the kind of waves we're looking at? Well, we're looking at waves that come from simple harmonic motion, and so this is going to be a cosine graph. Okay. And then in this kind of graph, what is this distance called? What? Period. Yep, good. And the other thing we can look at is we can look at position versus x, okay? This represents all the points along a one-dimensional wave's path. At a single instant. okay? So when you're graphing a wave, you have to choose whether you want to track the motion over time of a single point along the wave, or whether you want to track the motion of all the points, but only look at it at a single instant in time, okay? And when you, the first thing you should do when you look at a graph, okay, and what makes this even more complicated, what does this graph look like? It looks like a cosine 2, possibly with a different, you know, not the same frequency and stuff. And what is this called? Wavelength, yep. And so the first thing when you're talking about waves, the first thing you need to do when you see a cosine graph is make sure that you know whether you're talking about position versus time for a single point along the wave, or whether you're talking about position versus x at a single instant in the wave's development, okay? So in talking about how waves combine, let's think about a single point along the wave's path and how it changes in time, okay? For a combination of waves, think of position versus time graphs for a single point along the wave's path. And in terms of like hearing applause at an event, this single point that we would be talking about would be the point in your ear where your brain is taking the signals from, okay? So these waves are coming in. That point on your ear is the path of a bunch of these waves, and the sound that you hear is the combination of all those waves just at that single point, okay? Any questions about anything I'm saying so far? Okay, so how do they combine? So combination of the waves is called superposition, which is a math term. It's a really cool term, isn't it? Like it sounds like I don't know. It sounds like something you want to say a lot if you want people to think you're smart. But superposition just means adding. And superposition comes up in a lot of things. It just means that the total effect is the same as adding up the individual effects. Okay, so if the position, okay, so let me draw a picture here. Okay, here's you. It even looks like you. I'm just kidding. That doesn't make sense to say that to 20 people at once. Yeah. Okay, so here's you, and there's two waves coming in. So one's coming in from there, one's coming in from there, and they're meeting at your ear. Okay? So this is, so let's say your ear is point A, okay? And let's say this is wave 1, and this is wave 2. So this is a graph of position versus time for wave 1 at point A, okay? And let's say this goes like this, okay? With values of, let's say, 0.01 is the amplitude. So this would be negative 0.01. And then the other one looks like this. That's wave 2, graphed position versus time at point A. And let's say this is 0.005. Then the sound that you hear is the total wave at point A, which looks like it has a squiggly part over, the squiggly part comes from this second wave. The overall pattern comes from the first wave, and it's going to vary between 0.015 and negative 0.015. Okay, let's look at a couple in Excel so we can actually see what it looks like. Any questions about this yet? So all you do is at each individual point, you just add up what the values are. Like at this, when time is equal to 0, you take the 0.01, add it to the 0.005, and you get a value of 0.015. Okay, so let's, so here are the two waves. So first of all, let's see. I'm going to take two waves that are exactly the same, okay? So let's change this to 1, drag this down. Wait, what happened? Okay, so this is a graph of just cosine of where omega is equal to 1 you get a shape like this. This one, let's first start out by making them exactly the same graph. So all right. So what you get here, if this is wave 1 and this is wave 2, at every point you're just going to be adding 2 times whatever the value is, right? Because you have these 2 different graphs. You're adding, so when time is equal to 0, you're adding 1 plus 1. When time is equal to this, whatever this is, a little bit less than 2 seconds, you're adding 0 plus 0. And so what you get is just a doubled graph. The shape looks just the same, but every value is doubled. So instead of having an amplitude of 1, you get a graph that looks the same that has an amplitude of 2. Okay? So that's the easiest case. That's when 2 graphs are totally matched up. And what you get here is called constructive interference. Interference is when the 2 waves add together, and the constructive part means you're getting an increase in the amplitude of the wave that comes from adding these 2. Okay? So now let's see what destructive interference looks like. Well, if I change this second wave to be, so say it's the same wave, but it's just starting at a different point where these have exactly opposite values everywhere. Then at every point, at every instant, when you add these 2 waves together, you get, so when time is equal to 0, 1 plus -1, you get 0. A little less than 2 seconds, 0 plus 0, you get 0. And so you get zeros all the way across. Okay? And so the effect of adding these 2 waves is that you end up with, if these were sound waves and these were graphs of the position versus time at your ear, no matter how loud these 2 were individually, and you'd be able to hear either one of them, the 2 of them together, you wouldn't hear anything. That's destructive interference, and that's what they try to do with noise-canceling headphones. Although they don't know what the sounds are going to be, so it's tricky, and they have to use like complicated statistics and stuff, but that's the idea. To cancel out a sound, you just need to produce a sound that is the opposite of it at every instant. Here's a little bit more, a more common scenario. So this first graph is a sound with omega equal to 1. Now this second graph, let's make the omega value for that second graph equal to 20. And this is sort of what I drew just a second ago. You get an effect like this where there's an overall pattern of the slower wave with a superimposed faster wave on top of it. And all of those you just get from adding the 2 values point by point, you know. That's what Excel's doing here. I have, you know, 1,000 points or something. And at each one of those 1,000 points, I'm just changing the cosine function and it's adding the two together. Okay. I want to show one other cool thing. This is something, if any of you play stringed instruments or have played stringed instruments, there's a funny effect you get when you're tuning an instrument. You hear it really clearly if you're tuning a piano, but unfortunately most people who play piano don't tune the piano themselves. You hire a piano tuner. But this is what a piano tuner listens for, actually. You don't listen for the, I'm told this, I'm not a piano tuner, but you don't listen for the notes, how similar they are. You listen for this fluttering effect that happens when the frequencies get close to each other. So say you play a C and then you play another C that you're trying to tune. When they get close to each other, you start to hear this fluttering of the two notes. It has to do with the superposition of these two waves. And you hear the note, but you also hear this light fluttering over it. And it gets more intense and faster as the two get closer together. And then as they get really close, they start to spread out into a gentler, and eventually they fade into that fluttering going away. And that's the effect that you're listening for to know that those two notes are the same frequency. So let me show how that happens mathematically. So let's say that here we have an omega value of 100. And let's say here we have an omega value of 100. Let's see, how many? Let's say 110. Okay. So these omega values, remember, represent frequencies. And so what I'm doing is choosing two frequencies that are different from each other, but not too different. Okay, like fairly close together, close enough that that you would start to hear that fluttering effect. And let's look at what the superposition looks like. And we're actually going to see what that fluttering is. I think this will work. Okay, so these are the two waves. I made the frequencies so fast that you can't really see. I mean, these are still just cosine waves, but they're just at a very high frequency. And when you add these two together, because of the constructive and destructive interference at different places, what you get is, so this thing has a cosine, has that doubled cosine pattern, but if you smush it in and look at the big picture, you hear loud parts and quiet parts. If I zoomed in on that, you'd actually see this doubled cosine pattern with one pattern on top of the other one. But when you pull out so that that double cosine graph is sort of obscured, you see the big amplitude things are loud, the small amplitude things are quiet. So the big amplitude things are the constructive interference, the small amplitude are the destructive interference, and you would hear that as something with a noticeable pitch, a noticeable frequency, but on top of that, you'd hear a fluttering going from the loud to the quiet. And that's what you listen for as a piano tuner, if you ever want to be a piano tuner. Now you know. You have to buy that tool, and then you have to listen for the fluttering. Any questions about that? Okay, this isn't really something that that there are going to be any problems on. But we are going to do a lab where you listen for those beats, it's called, listen for that fluttering sound. And so this is where it comes from. So if two position versus time graphs add to increase the total amplitude, it's called constructive interference. If two position versus time graphs add to decrease decrease the total amplitude, it's called destructive interference. Okay, any questions about that? So the next thing I want to talk about, and this is stuff that we'll do calculations for, is standing waves. And I'm going to talk about this in terms of stringed instruments. And the same principle is why, like, brass instruments or, you know, horns and stuff work. The math is slightly different, but it's the same idea. So think about a guitar. So I'm going to draw like a side view of it. And it basically looks something like this. Okay. And the string goes from here to here. This would be a really hard guitar to play, but move that up a little bit. Okay, so there's the string going from, it attaches down here and it attaches here. And when you pluck a guitar string, waves form in the string. And those waves are cosine or sine waves. So, okay, let me say it this way. You would hear a sound if a single cosine or sine wave formed. Okay, just a single, like, you would hear a very clear note and stuff, but you wouldn't find it to be a very interesting sound. It would sound like the note on a Casio keyboard or something, you know. And people pay a lot of money for expensive guitars and violins and stuff, so they don't want to hear that sound. And so the sound that you hear on a guitar It still has a note like a Casio keyboard does, you know, like you can identify the note. But that note is actually a combination of a lot of simpler waves. And those waves are added on top of each other through superposition, okay? And the sound that you like, you know, is one that just has a combination of waves at different amplitudes added together that just sounds good to your ear. And that's why people pay $1 million for a 3,000-year-old Stradivarius violin, and they don't pay $1 million for a Target plastic violin, you know? And so the question is, what are the waves that add up? And how, and after those waves add up, how do you still hear a single note from it? And so the answer is, so let me write something about this. The note you hear from a guitar string is the sum of actually infinitely many simple cosine waves. The lowest frequency wave in this sum is called the fundamental frequency. And that's the note you hear. So whatever the fundamental frequency is, that's, you say that's a D sharp or whatever, okay? That's the fundamental frequency. Infinite sign. All the other higher frequency waves in the sum I'll wait for you. I need to change the page. Okay, so all the other higher frequency waves in the sum are called harmonics. And they're what gives the instrument its sound quality. So if someone plays a guitar, a violin, or whatever, a bass, and they say like, oh yeah, it has a really open, woody sound, or, you know, those are the things that come from how those harmonics are combined. Nobody says, you know, like, I like this guitar because it can play a D sharp. Every guitar has the same fundamental frequency. It's the combination of these harmonics that determines how the character that one has versus another one. Okay, so what are the possible harmonics? So notice that, I guess I'm gonna do sort of a blow up version of that side view of the guitar. The string goes like this. Only certain waves are allowed because the string is locked down here and locked down here. Okay, those 2 points can't move. The other points can move. And so these are the waves that are possible. A wave that goes like this, okay? A wave that goes like this. A wave that goes like this, okay? In between those 3 waves, so each of these has like an omega value, a frequency. In between those frequencies, waves aren't possible because the string wouldn't land where it needs to at these 2 lockdown points, okay? And you can keep going with this. And these are like snapshots of the allowable waves. So the mathematical formula defining these allowable waves well, first of all, look at this for a second. So we're talking about a snapshot of these waves. What is it that determines what's allowable and what isn't allowable? Which of those 5 wave quantities determines what's allowed here? The wavelength, yep, that's exactly right. So the formula that determines the allowable wavelengths says the wavelength, and I'll say the nth wavelength because we're adding up a whole bunch of these, is equal to 2L over N for N equals 1, 2, 3, and keep going up infinitely far. So this formula determines what wavelengths fit between this fixed point and this fixed point. And let's just make sure that this works, okay? So for N equals 1, we have that the wavelength is equal to 2 times the length, okay, where this is the length. So the length is like the speaking length of the string, the length of the guitar. So the wavelength for the first one is equal to 2 times this length. So look at this biggest wave, just that single arch, okay? If we kept that going until it repeated the pattern, so if we kept it going for 1 period, it would have to go for twice this length, okay? So that fits into, this one that I drew fits into this pattern. The second one, the wavelength has to be equal to 2L over 2, according to this formula, which says that the wavelength has to be equal to L. And look at this second biggest wave that I drew. This one exactly repeats its pattern once over the length of that string. The third one, it's a little harder to visualize, but says that we go through 1.5 wavelengths in the length of this string, and that's this third McDonald's symbol I drew, okay? And it'll keep going like that, but they have to follow this formula. Any wavelength that doesn't meet this formula can't meet the requirements of staying fixed at this point and this point. Any questions about that? Yep. N is just like a stand-in number that says we're going to be adding up infinitely many. We're going to be adding up infinitely many of these waves, and the way you get them is by putting in the infinitely many integer values of n, or counting number values of n, I guess, just the positives. And so that doesn't mean anything physical. That's just how you get these infinitely many wavelengths. Any other questions?
So what exactly are you looking for in the what is the equation again?
Okay, so this gives you, yeah, so that's a good question. So where we're going is we're going to come up with all of the frequencies that this string can play. But we're not there yet. What we've done so far is we've come up with an expression for the allowable wavelengths. We're going to turn that expression for wavelengths into an expression for allowable frequencies. Okay? Because you could think of like frequencies as kind of for one thing, that's the way we describe sound waves, is in terms of frequencies. For another thing, we could use those frequencies to calculate omega values if we wanted to plot these waves out or something. The value of n equals 1 gives what's called the fundamental wavelength. So this single arch from here to here is the wavelength that represents the fundamental, okay? And that's the one that's going to correspond to the fundamental frequency. So now we want to find the frequencies corresponding to each of these wavelengths. And the way we're going to do that is we know that the wavelength is equal to V over F, right? So if we're talking about the nth wavelength, that's equal to the wave speed over the nth frequency. Each frequency corresponds to one of these infinitely many wavelengths. And so, in other words, the nth frequency is equal to the wave speed over this nth wavelength. And we have a formula for the nth wavelength. So the last thing we have to do is just figure out the wave speed along the string. How can we figure out the wave speed along the string? Well, last time I gave a bunch of formulas for wave speed for a transverse wave along a cable, and that's what this is. So, and it's a transverse wave along a cable. Yay! We know that one. So the wave speed is equal to the tension divided by the mass per length. That was given before. And now we can combine these two. And we get that, combine this with this expression for the wave speed, and you get that the nth frequency is equal to the wave speed times, okay, so the wave speed is this, times 1 over the expression that we just had for the nth wavelength. Okay, so, and let me say, so when n equals 1, it gives the fundamental frequency. That's the note that you hear. N equals 2, 3, 4, and so on. Give the harmonics. Which provide the sound quality. Okay, and so two different instruments sound different in the amplitude of these harmonics. Okay, like one instrument might have a really relatively loud 5th harmonic and 7th harmonic and 40th harmonic. Another instrument might have a louder 11th, and so that's how it works. That's how the sound quality changes, even though the note is the same. Let's think about the fundamental frequencies for a second, because if you look at this formula, it's sort of, it makes sense with the way a guitar works. Okay, so let's think about like a guitar. The fundamental frequency is 1 over 2L and let's think about it in terms of the following things. Okay, so F1 equals 1 over 2L times the tension over the mass per length square root. And what are some of the things that you know about a guitar? So on a guitar, first, the more massive strings give lower fundamental frequencies. And so picture what a guitar looks like. Even if you haven't practiced since yesterday or whatever, maybe you can still remember what your guitar looks like. So there are 6 strings on it. Up at the top are strings that are wound. They're thicker strings. They're more massive strings. And those are the ones that play the bass notes. And down below those are the thinner strings, less massive. And those are the ones that play the treble notes, the higher pitch notes, the higher frequency notes, okay? So that's one thing we know about a guitar. And we're going to go back and check all these against this equation that we have for the fundamental frequency. Another thing we know about the guitar is when it goes out of tune, you go up to the tuning machines and you tighten the string to make the pitch higher, and you loosen the string to make it lower, okay? So tightening the string raises the frequency. And the last thing that you know is in order to, like you know from watching, you know, like Eric Clapton or whatever, like when you play the high notes, you're like playing down here, and then you like stand to the front and you bring your hand all the way in here, and those are the really high notes. And your hand is way up here. You're making the string shorter, right? That's what you're doing by holding the string up here. So we also know that shortening the string makes the fundamental frequency go up, okay? After midnight, right, that's an Eric Clapton song. So shortening the string makes the fundamental frequency go up. Okay, so let's check the first one against this formula. More massive strings give a lower fundamental frequency. So those more massive, thicker strings have a higher mass per length, okay? If everything else stays the same, then we have a bigger value in the denominator, and that means that the fundamental frequency is lower, okay? So that one checks out with the formula. Tightening the string raises the frequency. So if all these other things stay the same, but the tension goes up, the tension is in the numerator, and so that should raise the fundamental frequency. And from experience, you know, with a guitar, that's how it works. So that checks out. Shortening the string raises the fundamental frequency. So in that case, all of these would stay the same. The L would get smaller. It's in the denominator, and so that's going to raise the fundamental frequency, and so that one checks out. So this formula has some connection to intuition, okay? This formula tells you what goes into making a certain note on a stringed instrument. All the other ones are, so when you're talking about what note you're playing, remember that's the fundamental frequency. All of those other infinitely many ones that are added into the wave, those are sort of coloring notes. That they don't define the note you hear, they just define how it sounds. That's why you can tell the difference between a plastic guitar and a real guitar, you know. I know you're trying to act like you don't care about this, but this is cool. I don't care what you say.
Do the other harmonics come from the vibration of the wood?
Well, okay, so that's a good question. So like what we're talking about now is the string, right? And the string really, you know, you don't pay a lot of money for strings. Maybe the string is the important thing, you know, like maybe the guitar doesn't matter. But what the wood does is the string vibrates the wood. So the string is the first thing telling the wood how to vibrate, okay? But then the wood has certain vibrations that it can do well and can't do well. You know, can do easily and can't do easily. So the string sends all of the signals for all of these harmonics to the wood. The wood dampens some of those and projects some of those. And so the string sort of sends the wood all these options of vibrations that it can produce sound waves from. And the wood picks and chooses the ones that it's good at doing. So, and so that's why we're only talking about string properties here, but the wood of the guitar is what actually produces the sound wave that you hear. If you've ever had the experience of playing an electric, like a solid electric guitar without plugging it into an amplifier, you don't hear, it's really quiet. And that's because the string really doesn't, all you're hearing is the string essentially. With an acoustic guitar, what you're really hearing is the string making the top vibrate. And then that top vibrating is what sends out sound waves into the air. Does that make sense? Any other questions about this? Do you know that literally, like people take out like mortgages for like and I'm not talking about like billionaire collectors. I'm talking about like musicians who don't make a lot of money and play in some symphony orchestra, take out a mortgage for $500,000 or whatever to play a violin from 1750 or whatever. And they have it insured and, you know, it's amazing. One of our kids plays with the daughter of a violinist in the, what's the orchestra? I think they're still on strike. It's been horrible. Is it Minnesota Orchestra? Yeah. Well, she plays with them. Hopefully you will again. But yeah, her violin is from like the 1700s. From some Italian, not Stradivarius, but some other Italian guy from the 1700s. Okay, so here's the kind of question that, okay, so to calculate the frequency associated with each n value. This is the kind of question that you're likely to be asked about this. You'll be given these equations. So you won't be given that equation for the frequency because to me, I think these other three equations are kind of more, well, they're more like fundamental equations. They're more connected to intuition. So I think it's important that you just get comfortable combining these. So you'll be given these three equations on a test. First, you'll be given the equation that says the nth wavelength is equal to 2L over n. Second, you'll be given the equation that says wavelength is related to wave speed and frequency in this way. And third, you'll be given the equation that says the wave speed for a transverse wave on a cable is the tension divided by the mass per length. And here's an example question. So given that a string has a tension of 100 newtons and a mass of 0.01 kilograms and a length of 0.6 meters. What's the fundamental frequency? And second, what's the frequency of the sixth harmonic? Okay, so to calculate either of these, we need to know the wave speed. So the wave speed is 100 over the mass per length, square root. And so you get a value of 77.46 meters per second. For the fundamental frequency, the wavelength is 2L over 1. L is 0.6, so that's 1.2 meters. And so 1.2 meters is equal to 77.46 divided by the frequency, the fundamental frequency. And so the fundamental frequency is equal to 77.46 divided by 1.2. And so you get 64.5 hertz. Okay, so that's the note. Like you could Google, you know, guitar E string or something. Don't do that because that's the one string where there's two. But you know, whatever. You could Google some guitar string and frequency, and it would give you the frequency, and this might be one of them, although that seems unlikely. And then for part B, we're looking for the frequency of the sixth harmonic. The wave speed is still the same, but now we have that the wave length is equal to 2L over 6. So that's 1.2 over 6, which is 0.2. And 0.2 then is equal to 77.46 divided by the frequency of the sixth harmonic. So F6 is equal to 77.46 divided by 0.2. I can't do that in my head. Can anyone have a calculator? Thanks. So 387.3 hertz. And so all the harmonics are higher frequencies than the fundamental. If you think about that in terms of the superposition that we talked about, so let's see. So this would be the fundamental frequency, the lower frequency. The harmonics would be higher frequency. They look something like this. And the combined effect that you get is an overall pattern of the fundamental frequency with little undulations riding on top of it that represent the harmonics. Any questions about that? Nope. I don't really care what you round to. Okay, well, let's stop there, and next time we'll talk about energy transported by 3D waves, and then we'll move on to outer waves and on to the next thing.